So this lecture will look at the threshold voltage of the MOSFET. There is a bit of mathematics here, and if you are not familiar with the mathematics of the MOSFET and its physics, please don't worry about it, because we are not really going to use any of these equations later on. But it is important that we talk about it once so that you are familiar with the basics of it. Okay, so here is a band, what is called as a band diagram of a MOSFET drawn with on the right hand side is a p-type substrate, and on the left hand side is when one approaches the semiconductor surface. So this thin line is a semiconductor surface, and when a gate voltage is applied, the bands bend down. So this is drawn for a p-type substrate, and so the Fermi level is closer to the valence band. And when a positive gate voltage is applied, because these are electron bands, they bend down. And there are more and more electrons, that is indicated by the conduction band being closer to the Fermi level. Okay, as I said, if you don't understand any of this, don't worry about it. Deep in the substrate here, the hole density, which is P0, the equilibrium hole density, is equal to the acceptor ion density, and it can be written as this Ni e raised to Ei minus Ef over kT, which can also be written as Ni e raised to phi f by Vt, where phi f is simply Ei minus Ef, well, Q phi f is Ei minus Ef. So E is energy, phi is a potential. So phi has the dimensions of volt, E has the dimensions of joule. So this is phi f over Vt, and so we say Na is equal to Ni e raised to phi f over Vt, which if we rewrite, we can write phi f as Vt ln Na by Ni. So this equation is significant, and that's all we really need to get from this whole slide. Okay. Now, as we saw last time, the threshold voltage of a MOSFET is defined as the gate voltage at which the electron density at the semiconductor surface becomes equal to the hole density deep in the substrate. Now, the electron density at the semiconductor surface, S for surface, can be written as Ni e raised to psi s minus phi f by Vt, where psi s is the surface potential. So if I go back, this is psi s. So if there was no gate voltage applied, all these bands would be flat, they will be horizontal. As the gate voltage applies, the bands bend. So when the band bending equals Q times psi s, no, I'm sorry, at any gate voltage, the band bending is Q times psi s. And when this Q times psi s equals 2q times phi f, that is the voltage called the threshold voltage. So when the gate voltage is increased, psi s will keep increasing from 0. When it becomes equal to 2 phi f, we say, well, that is a threshold voltage. So from equations, that comes out from here. So we say the electron density at the surface is equal to the hole density deep in the body, and when we equate these two, psi s turns out to be 2 times phi f. So this defines the threshold voltage. Okay, so this is the other equation we need to remember. Now we are back to our MOSFET cross section. If we apply Gauss's law to this red, what is called as a pillbox in physics terminology. So if you apply Gauss's law, and I am leaving this to you because I am sure you are very familiar with Gauss's law, we can write the equation for Gauss's law as Vg, which is a gate voltage, minus psi s, which is the electrostatic potential as the semiconductor surface, divided by Tox, which is the oxide thickness. So Vg minus psi s by Tox is actually the electric field here in the oxide. The electric field is equal to the charge enclosed by this pillbox divided by the epsilon in the oxide. because we are writing the electric field in the oxide. The charge enclosed is Qs, which is the charge enclosed by this pillbox. Alright, so this is Gauss's law. Vg minus Is by Tox is equal to Qs by epsilon naught epsilon ox. Qs, of course, is the charge in the S for semiconductor, and that could theoretically consist of both depletion charge, which is this fixed charge, and it could have inversion charge, which in this particular figure I have not shown. Alright, now this is the Gauss's law equation, but if we look at it carefully, we can rewrite this. So if we take epsilon ox T or epsilon 0 epsilon ox on this side, then we will get Qs is equal to epsilon 0 epsilon ox by Tox into Vg minus Is. This is nothing but the oxide capacitance per unit area. So Qs is equal to Cox into Vg minus Is. So incidentally, Qs is also here the charge per unit area. So this is just Q equal to Cv. Alright, so in fact Q equal to Cv comes from Gauss's law. And if we further rewrite this, or rewrite this differently, so you take Cox on the other side, Qs by Cox equal to Vg minus Is, then you can write for Vg as Is plus Qs by Cox. Alright, again another form of Gauss's law. Now we say, well, the definition of threshold voltage is that when the gate voltage is such that psi s is equal to 2 phi f, then that is a threshold voltage. So when psi s is equal to 2 phi f, Vg is equal to Vt, which gives us a definition of threshold voltage mathematically. So Vt is defined as 2 phi f plus Qs over Cox. Alright, now what is Qs? Qs, as I said, could be potentially be depletion charge plus inversion charge. Alright, now it turns out that at Vg equal to Vt, at the threshold voltage, when the electron density has just become equal to the hole density in the substrate, if one goes through the numericals, one finds that the inversion charge, Q inversion, is very small compared to the depletion charge. So we'll ignore the inversion charge in the definition of the threshold voltage. So we'll say at the point when Vg is equal to Vt, Qs can be approximately written as Q depletion. So we say the threshold voltage is defined as 2 phi f plus Q depletion by Cox. Alright. Now one can solve Poisson's equation for that MOS system and show, which we will not show, that the Q depletion can be written as 2Q epsilon naught epsilon Si Na into 2 phi f. That same 2 phi f appears here also. So this is the equation for the threshold voltage. Alright, as I said, if you did not understand any of this, don't worry about it. In fact, we will not even be using this equation, but it is useful to know that this is the equation for the threshold voltage. At least in this lecture, for the next few minutes, we will utilize this equation multiple times. So stated in words, the threshold voltage is the gate voltage that is required to create two things, two terms here, this term and this term. What is this? This is the surface potential must be equal to 2 phi f. So the gate voltage must create a surface potential 2 phi f, plus it must create a depletion charge given by this equation, I mean this expression. Alright, so that is what the threshold voltage is. Now it is useful to remember that if the acceptor ion density in this p-type substrate is higher, then a higher gate voltage is required to create an inversion layer. Alright, number one. Number two, if Cox is lower, alright, then a higher gate voltage is required. Now what makes Cox lower? Let's go back to what is Cox. Cox is actually epsilon 0 by Tox. So these, there is nothing well, at least we will not do anything with these two. but Tox is the oxide thickness. So what this is saying is, if Cox is higher, Vt is lower. Or I want to say it the other way. If Cox is lower, Vt is higher. For Cox to be lower, Tox has to be higher. What that means is that if Tox is higher, Vt is higher. Alright, so if the oxide thickness is higher, then a higher gate voltage is required to create an inversion layer. If the oxide thickness is lower, or if the oxide thickness is small, then the gate voltage required to create the same inversion layer is lower. Alright, that is all. Okay, now we'll look at two additional effects that affect the threshold voltage. One is called the body effect. So when we derived this equation, we had assumed that the body of the MOSFET was grounded. Alright, so this body was grounded, source was grounded, etc. Drain was grounded. We are applying just the gate voltage. Now suppose the body is not grounded. Alright, then what is the threshold voltage? It turns out that the threshold voltage expression gets modified if the body is not grounded. Very physically, qualitatively, you think about this. If the body voltage is negative, alright. Incidentally, one generally will not apply a positive body voltage to an NMOS transistor because that is P type, and if this is positive, then these two PN junctions will become forward biased and a large current will flow in the body, which we don't want. So generally, if a body voltage is applied, it is always negative. Alright, now if a negative body voltage is applied, then what turns out that the depletion layer becomes larger. Alright, or in other words, the surface potential becomes larger. So as a result, and again I am not going into details of this because the physics of this is very complicated, so I just kind of skimmed through it. We'll just look at this equation and leave it at that. That if there is a body voltage present, and in MOSFETs all voltages are measured with respect to the source, so we say if there is a source body voltage present, then the expression for the threshold voltage gets modified to this. So then additional term is added to the 2πf under the square root. Alright, that is all that happens. So the body voltage causes the threshold voltage to increase. If there is a body voltage present, we need to apply a higher gate voltage to create the same inversion layer. Now traditionally this is written, so there is a little bit of mathematics here. So what we do is, so this is a VT expression, we add and subtract to this expression this term and this term. So alright, so 2πf plus this term which is here minus this term. Alright, now if you look at the first two terms here, this is the threshold voltage without the body voltage which we had already derived, and so that is called as Vt0. Alright, so this is Vt0, and these two terms, this constant is taken out, 2q epsilon naught epsilon Si Na by Cox is taken out, and then we have square root of 2πf plus Vsb minus square root of 2πf. And this prefactor is called as gamma, and gamma is called the body effect parameter. So the threshold voltage when there is a body voltage present is written in this form. It is the threshold voltage without body voltage plus a term that is equal to this, where gamma is a body effect parameter. Alright, the one thing to remember from this is that as when a body voltage is present, a threshold voltage is larger. Well, to be more specific, for an NMOS, when a negative body voltage is present, the threshold voltage is larger. Alright, so VSB is positive, Vt is greater, and VSB positive means VB is negative. Alright, let's look at how the threshold voltage varies with length. So it turns out that the threshold voltage is a function of length. So let's look at this expression again. We said the threshold voltage is 2πf plus the depletion layer charge by Cox. Now let's look at these two structures. There are two MOSFETs. They are identical in every respect except that this MOSFET has a much smaller channel length compared to this MOSFET. Alright, and then some small gate voltage is applied, so there is a depletion region created here. In this, I have shown it without any gate voltage. Now what we see here in this figure is that if we look near the surface, about 2/3 of the surface already has a depletion layer charge present. Alright, and that charge is entirely due to the depletion regions of the P n plus junctions, the source body and the drain body junctions. Here, of course, this entire depletion layer charge is created by the gate voltage. Only the small region here, little bit here and little bit here, was already present without the gate voltage. So what this is telling us is that when we reduce the channel length, a significant fraction of the depletion layer charge near the surface is already present due to the source body and the drain body junctions. And therefore, the gate voltage necessary to create supply this depletion layer charge needs to be smaller, because a significant fraction of the depletion charge is already present. So the gate voltage needs to create only about 1/3 of the depletion layer charge would have been required, compared to what would have been required if there was no source body and drain body charge. In a long channel device, this source body and drain body depletion layer charge is very small, a very small fraction of the total charge required to create the inversion layer, and therefore this does not the depletion layer charge here does not affect the threshold voltage. All right. So what that means is that as L decreases, a smaller and smaller fraction of the depletion layer charge needs to be created by the gate voltage, and therefore the threshold voltage decreases as a function of the channel length. All right. This is an observed phenomenon, and this was actually noticed probably about 30 years ago. So here is a plot of the threshold voltage on the y-axis and the channel length on the x-axis. And what one sees is that as the channel length is decreased, keeping everything else the same, and one measures the threshold voltage decreases. All right. So this is a property of this specific type of MOSFET. Now there is a problem with this Vt versus L behavior, and the problem is that actually this is not necessarily a very illustrative figure, but there is a slope here, right? So this line I have shown as the nominal channel length. So this is the channel length at which most of the MOSFETs would be built. So let's say a 180 nanometer MOSFET technology, most of the MOSFETs will be built at 180 nanometers. There will be a few transistors built at a higher channel length. Nothing, of course, will be built at a lower channel length, because by definition of a 180 nanometer technology, the lowest channel length that can be fabricated in that technology is 180 nanometer. Any larger length can always be fabricated, but not a smaller length. Of course, for experimental purposes, people would simulate and get these plots. All right. Now the problem is that as you see, okay, so here is what happens when one fabricates MOSFETs. Let's say in 180 nanometer technology, there is always small variations due to fabrication uncertainties, so that if you have built 1,000 MOSFETs and you had designed them to be built all at 180 nanometer channel length, when we actually build them, the actual channel length would vary by about 2 to 3 to 4% from this nominal value of 180 nanometers. So this 1,000 MOSFETs would have channel lengths that would vary, let us say, from about 175 nanometers to 185 nanometers or so. Now what this plot is telling us is that as the channel length varies, the threshold voltage varies. And as I said, this is not necessarily a very representative picture, but let us say this was a nominal channel length. Then you say the slope is very large, which means that for small changes in the channel length, the threshold voltage can have a large change. Now this is extremely undesirable, because if the threshold voltage varies unpredictably, right, we have no idea what the actual channel length will be between 175 and 185, and a threshold voltage is varying significantly, then designing circuits with such a MOSFET whose threshold voltage is so unpredictable is extremely difficult. It is extremely difficult. And so of course people realize this, perhaps I would think about 30 years ago, maybe roughly. And so the fact that the threshold voltage varies was not acceptable. So people said, well, we have to do something so that the threshold voltage does not vary with the channel length at the nominal channel length, okay, because that's where most of the transistors will be fabricated. So people came up with this idea of pocket implants. So let us talk about this. So what one does, okay, so the one thing one realizes is that, as we saw, if the doping is higher, then the threshold voltage is higher. Alright, and what we want to do, so let's go back here, I'm sorry about this. What we want to do is we want the threshold voltage to not become lower. Alright, we want the threshold voltage, okay, we'll see what we want actually. So what the solution to that problem was that people figured out that if we have the acceptor doping near the source and drain, here, only at these corners, alright, not throughout the region, but only near the corners here and here, if that is made higher, alright, if that is made higher, then this is how the depletion layer would look like when no voltages are applied. So you can see depletion layer, okay, in case you are not aware, the depletion layer is thinner if the doping is higher. So if the doping, the p-type doping here is lower than the p-type doping here, and so the depletion layer is thicker here and depletion layer is thinner here. Alright, because the p-type doping here has been made higher. What this does is that as channel length is reduced, the fact that you have a higher p-type doping at the source and drain ends will prevent the threshold voltage from reducing at that channel length. Eventually, if you keep on reducing the channel length, the threshold voltage will again fall, because the effect of this will still be only partial. As a result, so if we do this, then so let's say plot of this. So if we do pocket implants, then what happens is the threshold voltage actually increases as the channel length is reduced, because these pocket implants are only at the corners of the source and drain and they are higher, and so when their contribution becomes significant, the threshold voltage will increase, and then again it will start dropping when the channel length is made even smaller. Now again, if this is the nominal channel length, then what we see is that at this nominal channel length, the slope of the Vt versus L plot is 0. Alright, because here there is a maximum in the plot, and because there is a maximum, the slope is 0, and because the slope is 0, small variations in the channel length due to process variations will cause a very small variation in the threshold voltage, and therefore the circuit design becomes much more doable, much more predictable. Perhaps that is a correct word. Alright, so that is what is done. Alright, okay, this is it. This is a short lecture on threshold voltage. Next lecture we will talk about the current voltage characteristics and models for the MOSFET.